process I showed last time. We'll go through lots of graphs today. You'll have lots of chances to graph in class. Jessica and I will walk around and point you in the right direction. Thursday was kind of, a lot of stuff. We went through all 6 graphs, but we didn't get to do a whole lot of examples because you kind of have to know some steps before you can do anything. And so we ended up not doing a ton of examples. Today, though, we'll catch up with lots of examples. The first thing I want to do is catch some of the end of 6.5. We did most of 6.5, but there's this one last little nuance with odd and even functions. And this property, when we graph trigonometric functions, we'll see that it's kind of helpful. In college algebra, when you had a leading minus sign, what did that indicate to you in terms of a transformation? Mm-hmm. That was a reflection. And whenever we have a reflection, we have to decide whether it's a vertical reflection, which is through the x-axis, or a horizontal reflection, which is through the y-axis. And is a minus on the inside indicating a horizontal transformation, a horizontal reflection, or a vertical reflection?
Horizontal.
Horizontal. And one way to remember that is that the other one is vertical, and most of you are really comfortable with the minus that's out in front of a function. That's going to be a vertical reflection. Everyone good with that? Like if you have y equals x squared, and you put a minus in front of it, you have y equals negative x squared, which opens down. So that leading minus is going to do a reflection through the x-axis. That's a vertical reflection. And in general, the transformations that are on the outside of the function are all vertical, and the ones that are inside are all horizontal. So if you look inside the parentheses, that's where you see the horizontal shifts, the horizontal reflection. Oh, I just went like that for horizontal. Horizontal reflections. Now what we're going to see in a minute here, which is really nice, is that with trigonometric functions, you can always eliminate horizontal reflections. With algebraic functions, you couldn't do that. With polynomials, if you had a minus on the inside, you couldn't always get rid of it. But we'll see here with trigonometric functions, it's really easy to eliminate a leading minus, and then you don't have to deal with horizontal reflections. You only have to deal with horizontal shifts, which is kind of nice. And period adjustments. And period adjustments. So recall that the definition of an even function is a function that satisfies this property right here. And what that means, and the way I want you to think about it, is that the y value at negative x is the same as the y value at x. So that's how you should be thinking of an even function. The classic even function is y equals x squared. Right? Y equals x squared. It's a classic even function. And the idea behind this mathematical statement right here, if you imagine the origin, if you go to the left and to the right, the same distance, the y values match. That's what it means to be even. You're going to be symmetric about the y-axis. If you go left and right from the origin, the same amount, and that's what they're indicating here by having an x and a negative x, they're indicating that you're going 5 and negative 5, or 10 and negative 10. You're going the same distance from the origin, and then f of x and f of negative x are equal. So that says the y values are the same. And that's totally logical, right? If you think about y equals x squared, if you wanted to define what it meant to be even, you would say, oh yeah, if I go either way, the same distance, the y values are matching. We're at the same height. Okay, so that's our definition of even. Similarly, our definition of odd, what that says is that if you go the same distance from the origin, one y value is positive and one is negative, but the same magnitude. And the classic function that you studied in college algebra that was odd was y equals x cubed. Y equals x cubed was your benchmark odd function. If you go to the right one or go to the left minus one, the y values are the same in magnitude, but differ in sign. One is up, one is down. Okay? So that's the definition of odd. Same distance right and left, go up one, go down. Go up on one side, go down on the other side. So whatever it is, they're opposites. Okay, so let's take a look at the trig functions for a moment. And with the trig functions, let's focus on the unit circle. And let me pick a point on the unit circle. And we've learned so far, if this is theta right there, we've learned that the coordinates of this point, if you're on a unit circle, this is our really big insight from last week, that the coordinates of that, again, I call it a terminal point. It's a point on the terminal ray that intersects the unit circle. I call it a terminal point. So the coordinates of that terminal point are cosine theta, sine theta, if you're on a unit circle. That was our big takeaway last week. That's what the trig functions all boil down to. If you have a unit circle, if you know the coordinates of the points on the unit circle, you know all 6 trig function values. So there's theta. Now, minus theta would be down here. We'd rotate clockwise, and we'd rotate that same amount. That would be minus theta. And again, our takeaway from last week is the terminal point has coordinates, cosine of whatever angle got you to that terminal point. So this would be cosine of minus theta, comma sine of minus theta. Oops, there's supposed to be 2 right parentheses there. All right? Any question up to that point? So whatever angle gets you to a terminal point, the coordinates of that terminal point on the unit circle, cosine of that angle, sine of that angle. Doesn't matter how many times you rotate around, doesn't matter if you go clockwise or counterclockwise. Whatever angle gets you to that terminal point, coordinates, cosine, comma, sine of that angle. It should be pretty obvious, I think, that those 2 terminal points, black might not be the right choice there, the x value for both of those is the same. Do you all agree that both those terminal points have the same x value? Right? So that tells us, just by looking at that picture, that cosine of theta, cosine of negative theta is the same as cosine of theta. Agreed? If those 2 terminal points have the same x value, that means cosine negative theta and cosine theta are the same. So that's how we make this conclusion, that if you have cosine of negative theta, you can just erase the minus, because cosine of negative theta and cosine of theta always the same. Similarly, if we look at the y values here, we see that the y value right there and the y value right here are the same in magnitude. They have the same length, if you were to measure those segments. But sine of negative theta, in the picture I've drawn, is negative, and sine of theta, in the picture I've drawn, is positive. So that tells us that sine of negative theta is minus sine of theta. So those are going to be our 2 key facts that will help us with any time there's a leading minus on the inside of a trigonometric function. Sine is odd. The minus sign jumps to the front. Cosine is even. The minus sign disappears. So cosine is an even function. Sine is an odd function. Now, tangent of minus theta is sine of minus theta divided by cosine of minus theta. In other words, it's minus sine of theta divided by cosine of theta, which is minus tangent of theta. So that makes it odd. And if you look at that graph for tangent that we saw last time, Actually, the graph looks a lot like that, except there's asymptotes. The graph of the first period of tangent look like that. And the y-axis is right down the middle here. And that's, kind of what you think about with an odd function. Go up and down the same distance for x and minus x. And so here, I'm just thinking about division. Tangent of minus theta is sine of minus theta divided by cosine of minus theta, which is equivalent to minus sine theta divided by cosine theta. And sine theta divided by cosine theta is tangent, and then the minus drops down. And now we just have to reciprocate. So the reciprocal of minus sine theta is minus cosecant of theta. The reciprocal of cosine is secant. The reciprocal of tangent is cotangent. And that allows us to make the conclusion that, oh, this one is definitely odd because the minus jumps to the front. This one's definitely even because the minus disappears. And that one's definitely odd because the minus jumps to the front. So they're all odd except for cosine and its reciprocal secant. Otherwise, they're odd. So for odd, minuses jump to the front. For evens, minuses disappear. And here is how we will use those. Let's suppose that we have this tangent expression. Well, one thing, and I mentioned it last time, we'll see it a lot today, is that if we were to graph this, the first step is to factor the leading coefficient, which is negative 2x, to the front of the angle. We want to factor our leading coefficient. So if we factor that leading coefficient, negative 2, everyone agree on this factorization? Negative 2 times x is negative 2x, which is what we started with. Negative 2 times negative 2 pi is 4 pi, which is what we started with. So that's the correct factorization. And then because tangent is an odd function, that minus sign jumps to the front. Because tangent is odd. So if we have a leading minus for an odd trig function, just jump the minus to the front. If it's an even trig function, just erase it. And that is going to be a lot easier to deal with instead of dealing with horizontal reflections. It's always easier to deal with vertical reflections. We're much more comfortable with that. And summary, even functions have graphs that are symmetric about the y-axis. And then odd functions have graphs, we say that they're symmetric about the origin. And symmetry around the origin is displayed right here with y equals tangent x. Symmetry about the origin means if you go left and right the same amount, the y values are opposite in sign but the same in magnitude. That's what it means to be symmetric about the origin. Here's a picture of y equals sine x. That's an odd function. If you go left and right the same distance, you go up on one side and down on the other, the same magnitude. Even function, we go up the same distance if we go same distance from the origin. Y values match. Any questions on odd even? Ringing a bell? Loud bell? All right, let's see what we can do with that. So now what we're going to do is look at the worst case scenario, or maybe I should say best case scenario. We have a function, sine of x, that's got all the possible transformations at once. So you can think of that as a grand opportunity to explore all four types of transformations. All right. I guess there's more than four, but there's four coefficients that affect those transformations. The a in that up there has two transformations built in. If that a were negative, there'd be a reflection and a vertical stretch or compression. We'll get to that. Okay, so first always, factor first. That's going to be our first step. If you factor, you will be able to see the horizontal transformations very easily. If you don't factor, it's going to be a little harder. So we factor first, and once we factor, we have all these things going on. The transformations on the outside, the A and the D, we have the vertical shift. That's the easiest one typically for folks. And out in front, we have the coefficient capital A. The absolute value of that gives amplitude. In last class, we talked about amplitude. It's the maximum distance from that horizontal center of the graph, the center line. Amplitude is the maximum distance above or below the center line. That's going to be the absolute value of A. Amplitude is always a distance, so it's always positive. So amplitude is the absolute value. If that coefficient out in front happened to be negative, we would also have a vertical reflection. The B, it's moving left to right, the B on the inside, whatever that number is, we divide it into the period of the basic function, and that will give us the period of the new function, the transform function. So back in college algebra, you called that a horizontal compression or a horizontal stretch. And it had the opposite properties as A. If I have a number out in front that's bigger than 1, does it vertically stretch or vertically compress the graph? If it's bigger than 1 on the outside. So like, if you think about in college algebra, you dealt with x squared a ton. So y equals 2x squared. If you had y equals x squared, what is y equal 2x squared? Is that a vertical stretch or is it vertical compression?
Vertical stretch.
Vertical stretch. If that number out front is bigger than 1, you're stretching it vertically. Right? Do you see that a vertical stretch is actually the same as a horizontal compression? If you take y equals 2x squared, you're stretching it vertically. You could also look at that and say, hey, wait, aren't we compressing it horizontally? Yeah. All right, so vertical stretch and horizontal compression are actually the same. They're equivalent. But what I want to focus on is that B. So on the outside, if the coefficient is bigger than 1, we're vertically stretching. On the inside, if that number is bigger than 1, are we horizontally compressing or horizontally stretching? If that number is bigger than 1. Right there. And you can kind of get a sense by looking up here. So right now, sine has a period of 2 pi. Let's suppose B was 2 for a minute. If this was a 2 right now, let's just let B be 2 for a moment. The period of the transform function would be what? Be pi. So if the period went from 2 pi to pi, would that be a horizontal compression or a horizontal stretch? Compression. Right? Compression. So when the number on the inside is bigger than 1, it's a compression. Okay? But the number on the outside being bigger than 1 is a stretch. I just got through saying that a vertical stretch and a horizontal compression are the same. So if you kind of keep that in mind, it's like, oh, if the number is bigger than 1 on the outside or bigger than 1 on the inside, you have that equivalence. You have a vertical stretch, which is the same as a horizontal compression. It's bigger than 1. And the opposite goes for a number that's fractional, if it's between 0 and 1. Between 0 and 1 on the outside, compresses, vertical compression. Y equals half x squared, it's flatter. And same on the inside. If you have a half out there, plug in a half right here, and what is your period if B was a half? It would become 4 pi. 2 pi divided by 1/2. Half goes into 2 4 times, or 2 times 2 is 4. And so that's a horizontal stretch. So a horizontal stretch and a vertical compression are equivalent. So if you have a fractional coefficient in there, it's going to be the other way. It's going to be a horizontal stretch. Okay. So that's just an overview of how we can analyze these transformations that are built on top of a basic function. So let's go ahead and I'll walk you through a couple first, and then you guys can start. So we'll start with sine and cosine. Those are the easiest two. And always, if you're to graph the transformation of a trigonometric function, first thing you want to do, factor the angle. So get into the habit of these steps, and it will be very procedural. Those of you that did really well in college algebra generally do really well in college algebra because you're good at procedure. You're very good at following the steps. Graphing trigonometric functions is that. We have very clear steps. There's a lot of trig where I can't say, oh, do step 1, 2, 3, 4, 5, and you'll get to the answer. This, follow steps 1, 2, 3, 4, 5, you'll get to the answer. So that's a nice thing about this particular subject for a lot of you, is that it's very procedural. You can actually follow steps. Step 1, factor the angle. So factor out that leading coefficient. And whenever you're not sure, just let me know. If you don't see that the factoring is what you think it should be, let me know. That pi in there just throws enough of a twist into it that sometimes you look at it and you say, really, is that how it factors? This one's not too bad. You always double check. You say half to x is half x, half to the pi is pi over 2. And always check that your distribution matches what you started with. Okay. When we graph, I'll always write down these five characteristics of the transform function. And I get them by reading left to right. I think I can just barely see it up there. Okay. So we're looking here. We're looking at our factored function. We know our basic function is cosine. We'll start with reflection. So we go to the outside, look to the left, and is there a reflection? No. There's no minus out there, so there's no reflection. So, no reflection. Amplitude. So amplitude is always the absolute value of the leading coefficient. Amplitude is the absolute value of 1, which is just 1. So amplitude is 1. So that tells us that if we look at the center line, the horizontal center line of the graph, we go at most 1 up and at most 1 down from the center line. So that's giving us our maximum distance of travel from the center of the graph. Period. We start with the basic period of cosine. So that's 2 pi. And then we divide by the coefficient of the angle. We divide by b. So that's dividing by 1/2. That gives us 4 pi. So that's our period. So this is a horizontal stretch. Basic period's 2 pi. The period of this transformation is 4 pi. So we've stretched out the graph. Horizontal stretch. All right. The phase shift. PS. Phase shift. That's just fancy lingo for horizontal shift. Just like you did in college algebra to see the horizontal shift, you go to the innermost set of parentheses, and the horizontal shift is opposite of what you see. We see an addition of pi, so the phase shift is actually left pi radians. So I'll just indicate that by putting a minus pi, the minus meaning you're going to shift to the left. You could say shift left pi if you want, but that's going to be how I'll write it. That means a negative shift means to the left. And then vertical shift, we look to the outside. I tend to write that vertical shift over here. Sometimes the book will put it in front and write like 2 plus cosine. That seems strange to me. I'd put it on the outside because it comes last. It's the last thing you're going to do when you graph your function. Shift it up or down. But there's none. There's no vertical shift. And all of these, I will ask for the domain and range, but we're going to graph it first before we answer that question. But it's, whenever we deal with functions, we always have that sort of lingering. What's the domain? What's the range? So we'll get into the habit of always making that conclusion. But we want to graph it first. Okay, so last time I gave you an order to these steps. Sometimes they vary a little bit, but not much. So phase shift is always first. And the phase shift is minus pi. So that's where we're going to draw. Our goal is to kind of set up goalposts. We want the left edge of the first period and the right edge of the first period. We have to set up these goalposts for the function to be graphed in between. So this tells us that the left end point, the left edge, of the first period of the transformation is at minus pi. So we're going to put that on our graph, minus pi. And we've got to put a y-axis in here. I haven't put that in yet. But before I put the y-axis in there, let's take a look at this period. So if the left end point's over at minus pi, and the period is 4 pi, what does the right end point have to be? Has to be what? 3 pi. Because we're starting at minus pi, and we're going to go 4 pi to the right. So that tells us that our right endpoint is over here at 3 pi. So now we can see that, okay, I need 4 subintervals here. So the one that corresponds to the y-axis is going to be right there. So we're always going to subdivide the distance between the left endpoint and to the right endpoint into 4 subintervals of equal width. Those represent quadrant 1, quadrant 2, quadrant 3, quadrant 4. So if you put your left endpoint and your right endpoint and then subdivide, then you can kind of put your axis in. That helps a little bit. Often it's easy enough just to draw the axis in because they're going to give us nice enough numbers, but sometimes it's a little tricky. Okay, so we took care of the period. Now let's take a look at the amplitude. Actually, let me take that back. This has no vertical shift. Let's take a look at the vertical shift. That should come next. Because what we need to know, I want to graph the center of the graph. I want to know, is the center of the graph on the x-axis, or is it above, or is it below? Before we can apply the amplitude, we need to know where that horizontal line is, where the center of the graph is. Because the amplitude is based on where that line is. Amplitude tells us how far above and below that line. So vertical shift, there is none. So that tells us that our horizontal center line is right there. The graph is going to be based around right around the x-axis. Now we go to the amplitude. That's number 4. That tells us how far above and below. So this tells us our tick marks on the y-axis. We only need to go down to -1 and up to 1. And off on the side, I'm going to think about the shape. The shape for cosine, if we look at the first period of cosine, that's what it looks like. The shape of cosine is this, and it had these 5 key points if we go back and look at the graph of y equals cosine x. So that's the shape. And the shape will be the shape of the basic function. And then we'll apply the transformations to that. Okay, so now, got the shape. Before I start drawing points, I'm going to come over here and check. If there's a reflection, those key points are all going to reflect through the center line of the graph. If there's no reflection, those 5 key points will just match right up to the graph. So here we go. So we look at our key points. At the left endpoint, we have a key point that's up. At the right endpoint, we have a key point that's up. At the center, we have a key point that's down. And then at our 2 intermediate points right there, right on the center line. And we'll always get a V for the shape of a cosine. A V, the key points will always, a V or an upside down V for a cosine. Now we connect them. So just connect all these dots. And that is the first period of the transformation. It goes on forever in both directions, but this is the first period, and this is what I will ask you for in the test. This is the first period. The homework might ask you for 2 periods or something. I will ask you on the test for just the first period. And when I ask you for the first period, that means graph the first period. Don't graph 10 periods. Graph 1 period. If you want to graph more than 1, that's fine. but highlight the first period so it's crystal clear where the first period starts and where the first period ends. So on the test, that's all I want to see, but if you want to graph more, that's fine, but just make sure it's really clear to me which is the first period. Okay. And now let's ask these two ancillary questions, the domain and range. So after we've done our graph, it's a little easier to pop these answers in. What would the domain of a transformed sine be? All reals. Or the domain of a transformed cosine or sine. This is a transformed cosine. Either way, transformation of sine or cosine, domain is still all reals. Right? We haven't taken any numbers away from the domain. So all reals. And how about the range on this one? Yeah, this will be the same as the basic cosine, -1 to 1. We didn't have any vertical stretching. And we didn't have any vertical shifting. So just -1 to 1 for our range. Range, always a subset of the y-axis. Domain, always a subset of the x-axis. So any questions on that process? So this order here, I find, well, I'll label it, the first bunch of times we do this, but you'll hopefully get into the habit of that order. Let's do another one. So here we have a sine. First step is to factor out the 2. And I want you to look at that and make sure it's really clear to you why that factorization is correct. It's not hard, but it's very easy to make a mistake on that. And you don't want to make a mistake there because it will translate to mistakes later. As soon as you start finding other characteristics of the graph, you'll have propagated mistakes. To check that that's the right factorization, we distribute the 2 to the x, we distribute the 2 to the pi over 8. Pi over 8 times 2 over 1 is certainly pi over 4. But you need to get comfortable with coming up with a process for yourself to make sure you understand how you factor out a 2 from a numerator that has no 2. If you want to factor a 2 out of a numerator that has no 2, it'd be really easy if the numerator was, say, 2 pi over 3. Then you could say, oh, I just pull out the 2 and I'm left with pi over 3. That'd be really easy if there was a factor or a multiple of 2 in that numerator. The trick, though, is understanding when there is no multiple of 2 in that numerator. So if there's no multiple of 2 in the numerator, it forces an extra factor of 2 in the denominator. And if you're pulling out a 2 from 1, you get 1/2. So it introduces a 2 in the denominator as a factor. Everybody see that? So if I'm factoring out that 2, there's no 2 there, but what I could do is this. And this is absolutely fine. If you look and say, hey, there's no 2 in the numerator, put 1 in. Make it 2 pi over 8. Multiply top and bottom by 2 if you have to. If you need to do that to see, oh, yeah, now there's a factor of 2. Pull that factor of 2 out, and you get that. Totally fine. Right? If there's no 2 there, put 1 there. But if you put 1 in the top, you've got to put 1 in the bottom. Okay. So now we've factored, and we can go through our properties. Again, read left to right. There's no reflection. There's no minus out in front. Amplitude. That's the absolute value of the leading coefficient. So the amplitude is just 1/2. So right away, you should be thinking vertical what? Stretch or compression? Compression. Right? Vertical compression. Vertical compression. Period. What's the basic period for sine? 2 pi. What do we do with the 1/2? Divide it. So we do 2 pi divided by 1/2, so that is 4 pi. So, oh, whoops. That didn't work out right. We're supposed to be dividing by the leading coefficient of the angle. The leading coefficient of the angle is the 2, not the half. Right? The half is for the amplitude. The 2 inside there is the period adjuster. So I should be dividing by 2, not 1/2, getting pi. Okay, so 2 pi is the basic period for sine, and we divide by that period adjuster right there. And that gives us a period that's smaller than 2 pi, so we've horizontally compressed it. That number is bigger than 1, so that matches. Should be horizontal compression. How about the phase shift?
Plus pi over 8.
Yep. So it's pi over 8 to the right. It's opposite of what we see. So we see a minus pi over 8. So that tells us that we're actually going to shift to the right. We always shift opposite of what we see. If we see a minus, we shift to the right. If we see a plus, we shift to the left. So that shift is going to be pi over 8. And I'll indicate that it's a shift to the right by just leaving it with a plus, or no, if it's plus, you don't even have to put it. So that means shift to the right. If it's a minus, that means shift to the left. Okay? And then again, no vertical shift. All right, step 1, phase shift. So we have to draw a horizontal axis, and we have to put our phase shift on there somewhere. Now in this case, the phase shift is to the right of the y-axis, so it doesn't really matter where we put the y-axis. The y-axis becomes much more important if the phase shift is to the left of the y-axis, because then the y-axis has to fit exactly right inside that interval from the phase shift to the phase shift plus a period. But if the y-axis is out to the left, it doesn't. You can draw it so it's not to scale if you have to. If the phase shift is to the right, the y-axis can just sit there, and it's fine if this distance doesn't match the distances to come. No big deal with the graph. Okay, start at pi over 8. What's the second step? Period. Richard?
I just had a question. Kind of went back. When you got the phase shift, how did you get the pi over 8 without the negative?
So the phase shift is always the opposite of what we see here.
Okay.
So we see minus pi over 8, so the phase shift is plus pi over 8. Just like on this one, we see plus pi, but the phase shift is minus pi. So it's always going to have that pattern that it's opposite of what we see. And the phase shift for sine or cosine will always be the left edge, the left end point of the first period. How do we get to the right end point of the first period? Add the period, right? If we're starting here and it's a periodic function that repeats itself every pi radians, to get to the end of the period, we add the period. So we're going to take pi over 8 and add pi to it. And if you have to, it's like, oh, they don't have the same denominator. Well, make them have the same denominator. If that helps you, do it. You know, when you're dealing with arithmetic that doesn't have pi in it, it's a lot easier to see. If I say what's 1/8 plus 1, you can probably see that a lot easier than you can when there's a pi in it. If you need to write these intermediate steps, do it. So we have to add 8 pi over 8 to pi over 8, and that gives us 9 pi over 8. So that's right there. Pi over 8 plus 8 pi over 8 is 9 pi over 8. And then we have to subdivide this into 4 equal subintervals. So every time we do our graph for a sine or a cosine, we're going to have 4 subintervals of equal width in there. Now, on the homework, it's going to ask you for some of these subdivisions. Can anybody tell me what that midpoint is between the pi over 8 and the 9 pi over 8? What that point is right there? What that x value is? I hear a pi over 2. Is that what somebody said? Pi over 2? Anyone? 5 pi over 8, I hear. So the subinterval, so this x value right there, there's a few ways to get it. Let me talk about a couple of ways. Back in algebra, or even before algebra, you learned how to find midpoints. So this is one way. If your left endpoint, let's use integers. If that was a 2 and this was a 10, how did you find the point in the middle? What did you say? you see, the simplest way, the way you probably learn first, you add them up and divide by 2, because you're averaging. You're trying to find the, like if you have 2 exams and you want to know your average, add them up, divide by 2. And that's what we're trying to figure out. We're trying to find the average point in between. So we add, divide by 2, we get 6. It's 4 to the right of this, and it's 4 to the left of that, so it's right in the middle. So that's one way. That's probably the most intuitive way to find the midpoint, is to add and divide by 2. Okay, so that always works. So you could do that with pi over 8 and 9 pi over 8. So if you add those, you get 10 pi over 8. And that simplifies to 5 pi over 4. Now, you have to divide it now by 2. Dividing by 2 is the same as multiplying by 1/2, and that will give us 5 pi over 8 as that middle point. Right. So that's probably the most intuitive way. Another way is this. When we have our interval, we're going from pi over 8 to 9 pi over 8, and then we say, hey, let's subdivide it into 4 equal subintervals. You could say the distance between pi over 8 and 9 pi over 8 is pi. And if you're subdividing by 4, pi divided by 4 is pi over 4. So each of those subintervals is pi over 4 long. All right? Everyone to follow that? If this distance from here to here is pi, that means each one of these is pi over 4. We have 4 subintervals of pi over 4. Pi over 4. Right? So you would say to yourself, take pi over 8, add pi over 4, add pi over 4. Totally fine also. And what is pi over 4 plus pi over 4? You could certainly do the regular arithmetic. Pi over 4 plus pi over 4 is 2 pi over 4, which simplifies to pi over 2. One thing I hope you're starting to do is think geometrically. If you think about a unit circle, pi over 4 is right there. There's 0, there's pi over 4. And this is 2 pi over 4 up top on the unit circle. That's pi over 2. So pi over 4 plus pi over 4 is pi over 2. Right, so you think of it that way. So now we have to add pi over 2 to pi over 8. Again, common denominator, if you have to get it and write it down, do it. Multiply by 4 and 4. So we get 4 pi over 8 and pi over 8. You add those, you get 5 pi over 8. So there's lots of geometry, lots of basic arithmetic that looks harder because you have a pi thrown in there. So lots of different ways to get to that midpoint. All right. Step 3. So we've got our phase shift. We've added our period. So we've got our goalposts. The graph's going to happen in between. Now we need to know where this center line of the graph is. If there's no vertical shift, the center line of the graph is right there. Okay, there is no vertical shift. So the center line does sit right on the x-axis still. If there was a vertical shift, the center line would just shift down or shift up, whatever the vertical shift was. Next step, let's figure out how far above and below the center line we need to go. We don't want to start labeling our y-axis until we know how far below and how far above the center line we need to go. And the amplitude's only 1/2. So let's label positive 1/2 and negative 1/2. Now we have to deal with this thing that I call the shape. Write it up here. I'll always write it up at the top somewhere. And the shape is the first period of sine, in this case. And the first period of sine looks like that, and those are the 5 key points in the first period of sine. So if there is no vertical reflection, those 5 key points will just drop right into this little rectangle that we kind of see here. And some people will actually draw a rectangle between the amplitude, up and down from the amplitude, and over. If you want, you can draw a rectangle. The 3 key points right on the center line, those, even if there's a vertical reflection, those definitely don't go anywhere. They stay on the center line no matter what. If there's no reflection, the center point, the key point there, the high key point will stay as a high key point, and the other one will stay as a low key point. So there is no reflection, so those key points match like that. If there was a reflection, instead of up on the left, down on the right, we'd just switch those. So it'd be down on the right, down on the left, up on the right, if there was a reflection. Now we connect the dots. Woo. And there's the first period of our transformed sine. First period. Domain, all reals, range, minus half to plus half. Including the endpoint, so we put brackets. Brackets to include. Any questions on any step? Yeah, so.
How did you get 8 pi over 8? And also, how did you get 3 pi over 2 equal to 5?
Okay, so the 8 pi over 8, when you have the number pi, you can think of it as over 1. And I multiplied numerator and denominator by 8 to force it to have the same denominator as the phase shift. Because if they have the same denominator, then we can add those together really easily, because you have to have a common denominator to add. So I just took pi, and I found an equivalent form, multiplied by 1. Equivalent form, change the denominator just so you have like denominators, so we can add them. So the same was true for something else over here. Where was it? Right there, somewhere. Oh, here. We wanted to add these two numbers together, but to add these two numbers together, they have different denominators. So here we had to multiply by 4 over 4, so we had 8 in the denominator, so we could add them. So pi over 2 plus pi over 8 is the same as 4 pi over 8 plus pi over 8, which is 5 pi over 8, which was the middle term. Any other questions on that? Any step? Yeah.
So in between pi over 8 and 5 pi over 8, is pi over 4?
Great question. So let me remind you that we said that this whole distance here was pi, which if we subdivide it into 4 equal pieces, each subinterval is pi over 4. So what do you think that point would be up there? It's going to be pi over 8 plus pi over 4, right? So 2 pi over 8 plus pi over... Oh, wait, I said that wrong. So we would have to do pi over 8 plus, instead of pi over 4, let's make it 2 pi over 8. So it would be 3 pi over 8 right there. So that one would be 3 pi over 8. And that's what let me just say one thing about the way I drew this y-axis. I just threw it in, and that's what I meant when I said it might not be to scale, and it doesn't really matter. If I was trying to draw that to scale, I should actually draw it about right there, shouldn't I? So that this distance here is pi over 8, which would be half of that pi over 4 interval. So that y-axis, if you've shifted to the right, the y-axis kind of just floats out there, and it doesn't really matter because you're never really asking about the distance from the y-axis to the left endpoint. It matters when you shift to the left and the y-axis is in the interval. It really matters. Does that make sense?
How did you calculate it exactly? How did you get 3 pi over 8?
So 3 pi over 8, this from the y-axis to here is pi over 8. And that distance there is pi over 4. So we're going to add pi over 8 plus pi over 4. Do you agree that that's pi over 4?
Yeah.
So this is...
It's in the middle between pi over 8 and 5 pi over 8.
So the other way is to do the middle thing. You could say, oh, 5 pi over 8 plus pi over 8 is 6 pi over 8, which reduces, you could do that. Pi over 8, you're finding the midpoint, so pi over 8 plus 5 pi over 8 is 6 pi over 8, which reduces to 3 pi over 4, but then you have to divide by 2. And if you divide 3 pi over 4 by 2, you get 3 pi over 8. So you could do that. You could do this plus this divided by 2. That also works. Lots of ways to get that. So you could use the midpoint process, which would be pi over 8 plus 5 pi over 8, which gives 6 pi over 8, which reduces to 3 pi over 4. But then you divide by 1/2, which is the same as multiplying by 2, which gives you 6 pi. Oh, I did that wrong. If you're dividing that by 1/2, oh no, yeah, you're multiplying it by, oh, that doesn't make sense. Multiplying it by 2 gives 6 pi over 4, which is 3 pi over 2, but that's not what we have there. So there's some little mistake there. Hold on, let me erase some of this stuff. Let's start that process over. So if your goal is to figure out that point right there, that's going to be halfway between those two. So you would do pi over 8 plus 5 pi over 8, all divided by 2. That should give it to us. So that's 6 pi over 8 in the numerator. Dividing by 2 is the same as multiplying by 1/2. 2 goes into 6 3 times, so you have 3 pi over 8. I don't know what I did up there a minute ago. There's some small error in that.
Could you touch up again on how you got the period, the 2 pi over 2?
Period is found by taking the basic period for sine. So our basic period for sine is 2 pi. And then we're going to take whatever that coefficient is right there and divide it into the basic period.
I see.
So basic period divided by leading coefficient. All right, let's see. Why don't we? I want you guys to graph one now, but why don't we take a 10-minute break now, and then I'll write one up on the board that you guys can graph. And Jessica and I will come around and help you with that graph. Get your graphing perfected. So these properties here, these 5 characteristics, you're looking at the equation left to right, or looking at the function left to right. Reflection, there's no reflection, because there's no leading minus out there. And then amplitude is always the absolute value of the leading coefficient, so that's plus 4. It's always positive. It's a distance. It's up and down from the center. Period for sine is 2 pi. We have to adjust it with that number out in front. And now we need the phase shift. The biggest mistake is this. You look there and you write a pi. That is the biggest mistake, the most common mistake. You have to factor before you can see the phase shift. So we need to pull a 3 to the front. And over here, there's no 3 in the pi, so what you have to do is put a 3 in the denominator so that when you distribute, it works. When you multiply 3 by pi over 3, you get pi. So it gets you back to pi. So our phase shift is not pi, it's, what's the phase shift? Yeah, pi over 3. That's the phase shift. Opposite of what we see. We see a minus pi over 3, so the phase shift is plus pi over 3, which means shift to the right pi over 3. So we go to our graph, And this one's nice because the shift is to the right, which leaves the y-axis out of it, which is good. That makes it a lot easier when the y-axis is left out. So pi over 3 is where we start. That's step 1. Then we have to go to the right, the period. The period is 2 pi over 3. So 2 pi over 3 plus pi over 3 is 3 pi over 3, which is pi. That gets us to there. And now, it's very helpful to subdivide this into 4 equal subintervals. And I didn't ask this, but if you were asked to find the coordinates of or the x value of the midpoint there, what would you get? Yeah, go ahead.
Because x minus pi over 3 won't be negative pi over 3?
So the shift is always the opposite of what's here. So when we look up here, we see negative pi over 3, so that's going to be a shift to the right. And if we saw plus pi over 3, that would be a shift to the left. So that shift's always the opposite of whatever is there. Whatever we see minus pi over 3, that means the shift is actually to the right pi over 3, not to the left pi over 3. So it's always opposite of what we see. And how about that midpoint right there? Anyone know what that is? 5 pi over 6? Let's check. So we could do pi over 3 plus pi divided by 2. That would be the average of those two numbers. Now if I want to add the pi to pi over 3, I would write it as 3 pi over 3. So that would end up being 4 pi over 3 in the numerator. Dividing by 2 is the same as multiplying by 1/2. And we're getting 2 pi over 3. What did you say, Kelly? Did you say 2 pi over 3? No. Oh.
I didn't realize what was happening.
Yeah, it's really easy with these things to sort of, it's good to double check with a separate process just to make sure you're doing your arithmetic right. And the second process that I would use in my head would be this. I would say, okay, the period is 2 pi over 3. So from here to here is 2 pi over 3. Let's divide that by 4 and figure out what each of these individual subinterval widths is. So 2 pi over 3, if I divide that by 4, that's 2 pi over 3 multiplied by 1/4. 1, 2 cancels, and we get pi over 6. So each of these subintervals is pi over 6 in width. So that tells me to get from here to here, I've got to do pi over 3 plus pi over 6 plus pi over 6. Pi over 6 plus pi over 6 is pi over 3. Pi over 3 plus pi over 3 is 2 pi over 3. So that's a way to check. That also tells me that my y-axis is not to scale, too. So that this distance right here is pi over 6. Oh, actually, that's not too bad. Should go a little bit this way, though. So that distance right there is pi over 3. So it should be, yeah, about there. Okay. Now, third step, which is a new one. We didn't have a vertical shift in our last couple. The vertical shift is 2, so we're going to go up 2 units. So the center line of the graph, if we had no vertical shift, would be right there. But this graph does have a vertical shift of 2, and I'm going to draw those units right there. Shift that up. So that is the new center line of the graph. Up at 2. Then we're going to jump into the amplitude. We need to know how far above and below that center line we need to go. So we have to go up 4 units and down 4 units. So that takes us up to 6 and down to -2. So 4 units above, 4 units below. And we're going to apply the reflection as we put our key points on. So our key points, there's definitely 3 right on the center line. And normally we have a key point up at the left and down at the right. We check to see if there's a reflection. There's no reflection, so that will stay. We're going to be up at the left midpoint and down at the right midpoint. And that will be our first period then. Starting to make sense? Starting to feel a little better than overwhelmed, hopefully. The domain of this function, certainly all reals. That part's pretty obvious. How about the range? -2 to 6, brackets to include. Yep. Good. Excellent. All right, let's try another one. Let's go to the tangent. And on Thursday, I summarized this, but let's just go through some of the characteristics again, because asymptotes and counting asymptotes can kind of be a little bit tricky until you get comfortable with it. So here's a picture of tangent. The left asymptote to the first period is pi over 2. The left asymptote is minus pi over 2. The right asymptote is pi over 2. So those are the left and right asymptotes. And those asymptotes occur a distance of pi radians apart, which is why we say the period for tangent is pi. It repeats itself every pi. So if it's pi apart, then this over here is 3 pi over 2. That would be the next asymptote. And similarly, if we subtracted pi over here, we would get negative 3 pi over 2. That would be the next one that direction. So they're all pi apart. So for our domain, we say that x has to be a real number, but it's not allowed to be an asymptote. So we go to the first non-negative asymptote, which is pi over 2, and then we add the distance between consecutive asymptotes, which is pi, multiplied by k, which is our counter. It's going to count off the asymptotes. When k is 0, we're at this asymptote, just to the right of the y-axis. When k is 1, we're at this asymptote. When k is negative 1, we're here. And k has to be an integer. Okay? So it can't be, it can't be a fraction. It's got to be an integer. And so everybody see that when k is 0, we're at pi over 2. If k is 1, we have pi over 2 plus pi, which is 3 pi over 2, which is that one. If k is minus 1, we have pi over 2 minus pi, which is negative pi over 2. So for all integers, this will grab each of the asymptotes. And then the range for tangent's easy. It's all reals. Goes up forever, down forever. Okay, so let's do a transformation. That's our basic tangent. Oh, notice when we dealt with sine and cosine, the period started right at the y-axis. For sine, it went up, and it did. Let me just draw a quick little shape. Right, sine went like this, and that was right at the y-axis. Cosine does this, starts right at the y-axis. Tangent, though, notice that it doesn't start at the y-axis. Tangent has its first period around the y-axis. The y-axis is in the middle of the first period. It's not the left end point of the first period. So that's going to come into play in a moment, that difference. So note for tangent, the phase shift corresponds to the midpoint of the first period. This is the only function of the 6 that we have one slight difference with how we start our graph. With sine, cosine, and cosecant and secant and cotangent, we'll start right at the phase shift being the left endpoint. Only tangent is different, and here's how it's different. So first we take our tangent, the angle. We don't have any factorization to do in the angle. So we'll just start with our properties here. Yes, there is a reflection. I see the minus out in front. Amplitude. What's the definition of amplitude? What's that? So the definition is how far up or how far down it goes from the center line. The way you calculate it is to take the absolute value of the leading coefficient. So if we think about our definition, it's the maximum distance you go above or maximum distance you go below, and then you look at this graph, does it make sense to talk about amplitude for a tangent function? No, because this graph goes forever up and forever down, so there is no maximum distance this graph is from the center line for the graph. So when we graph and deal with tangent and cotangent, it doesn't make sense. It's not applicable to talk about amplitude for a tangent or a cotangent. Okay. The period for this transformation is the basic period for tangent, which we can see by the graph. The basic period for tangent is pi. But then we have to divide by the leading coefficient of the angle. But the leading coefficient of the angle in this case is just 1. So our period ends up being the same as for a basic tangent. It ends up being pi. So no horizontal compression or stretching. Phase shift? Pi. So positive pi, because we're going to shift to the right. We're going to do the opposite of what we see. We see minus pi, so the shift is to the right pi. How about a vertical shift? 2. You can answer the range question right away. What's the range of this transformation going to be? All reals. Doesn't matter how much you compress or stretch in either direction. The range is still going up to infinity and down to minus infinity. Can't change that. So we know that the range is going to be what it is. All right, so here we go. So we start with our x-axis. And you can put your y-axis on there if you want. It doesn't really matter. The nice thing here is that the shift is to the right of the y-axis. So phase shift is pi. So let's put that on here. So label that first. With sine or cosine, the next step would be to add the period to that. Tangent is different because tangent has the phase shift. If we shift this point to the right, that's going to be the midpoint of the first period. So we take our phase shift, put it on the graph, we take our period. That period of pi needs to be put on here so that the phase shift is the midpoint. Right, so there's our difference. So instead of adding pi, we are going to add and subtract pi over 2. Okay, so we're taking our period of pi, and instead of adding it to the phase shift, we're using the phase shift as a midpoint. Okay, so this is the only function that does this. All the other functions do it the other way. This is the one difference. Now I can move my y-axis so that it's scaled a little better. Right there. And for tangent, there are asymptotes at these endpoints. So I can put those in. So there's our first period. In between there. All right, so we still use the same order. We start with the phase shift. We go to the period. We just apply the period differently. Now we go to the vertical shift. It's 2. So we're going to take our center line, which would be the x-axis, if there was no vertical shift, and we have to shift that center line up. It's going to be right there. And our shape for tangent looks like that. And there's only one key point, and that's really right there. It goes up to the right with that one key point. So amplitude's not applicable in this case, so we ignore it and go to the reflection and the shape. Now the key point that we have there, that's still totally fine, right there, dead center. Now normally tangent goes up to the right, but we say, oops, there's a vertical reflection, so it's going to go down to the right. So it is going to look like, let me stretch these asymptotes up a little bit. So our graph is going to go down to the right instead of up to the right. It'll look something like that for our first period. So there is no amplitude, but what is true is if you look at that coefficient out in front of tangent, if it were large, like a 10, if it was bigger than 1, like 10, it's still going to do a vertical stretch. And if it was a fraction, like 1/2, it would do a vertical compression. But we really don't care about it. All I care about is that one key point there. If you want to try to indicate that it's flatter like that, if your leading coefficient was greater than 1, and less, oh, I said that backwards. If it was, this would be flatter, right? So that's less than 1. And if it's greater than 1, it's going to be steeper. It would look more like that. So that's if it is greater than 1. You can kind of do that if you want, but I'm not going to ask you for another point. Sometimes the homework might say, hey, pick another point on the graph. But for our graphs, if the coefficient's 1, something like that. It's not that's not going to be an important piece to our graph. It's the direction that it's going that's going to be more important. Okay, so domain of this function. It wants to be all reals, but it can't because we've got asymptotes, those pesky asymptotes. So we look and we grab the first asymptote, generally the first non-negative asymptote. X can't be pi over 2 plus how many k? Pi k? Because they're still pi apart. So that didn't change from the original tangent function. They're still pi apart. All right, so let me give you one to do. So when do you try that one? So I wrote that's 0.5x, that's just 1/2 x. If you want to write it as a fraction, that's totally fine, 1/2 x. Factor it out and see if you can get it. I'll put the shape over here, although it should be pretty obvious. Factor first, get that half factored out. Graph second. Almost done with our first chapter. Remember that tangent has no amplitude. So the A in our characteristic list here is amplitude. So that should have an n/a. It's not applicable for a tangent function. This tangent goes up and down forever. Leading coefficient has to stay the same as you factor it out. The coefficient of pi can change, but when you factor out a half, that's got to be the number out in front. Has to be 1/2. So I wrote the factorization up there. If you got the wrong factorization, you need an explanation. Let one of us know. Yeah, x plus 4 pi. 4 pi. 4 pi.
So to get p, that's the period, we take 2
Not 2 pi's. Just yeah. So the basic period for tangent is pi. So our period for this transformation will be pi divided by 1/2, not 2 pi divided by 1/2. So we always take the basic period of the parent function and divide it by the leading coefficient of the angle. So the basic period for tan is pi, divided by 1/2, you get 2 pi. How about the phase shift? So positive 4 pi or negative 4 pi? Negative 4 pi. It's to the left 4 pi. It's always the opposite of what we see. Vertical shift? Down 3, which we indicate with a -3. Range, if you want, you can fill that in right away. You know the range is still going to be all reals. Can't do much to stop that. So our graph, we're going to start with the phase shift like we always do, -4 pi. And then we go to the period. So we definitely start with the phase shift, then go to the period. And here is the big difference. So the period is 2 pi. Normally, you would add that to -4 pi. That's what you would do if it was a sine or a cosine. You would add the period to the phase shift. But that's not what we do with tangent. With tangent, it's a little different. Instead, we take the period and we use the phase shift as a midpoint. So we need to go to the left pi and to the right pi. So this whole period here is 2 pi, and that has to have the phase shift as a midpoint. Now it's a little bless you. Now it's a little easier to put your y-axis in here. Y-axis is going to be off to the right. It doesn't have to be the scale here. Doesn't have to be. If you want it to be the scale, we would have to make it probably a little bit more like that. Tangent will have vertical asymptotes at the left and right endpoints. Let's see, vertical asymptotes. We're going to apply our vertical shift next. If there was no vertical shift, our center line would be right there. But there is a vertical shift. And we need to go down 3. So 1, 2, 3. So down 3, that's going to shift this down 3. Maybe a little bit more. Something like that. And the key point from the shape, that's still going to be dead center. Amplitude makes no sense with the tangent function, so we go up to the reflection. That's our last step here. We look at our shape. We look at our reflection. There is a reflection, so instead of going up to the right, we're coming down to the right. So there's our graph. Something like that. We can now get our domain. This one it really doesn't matter in the grand scheme, and on a test, I don't care if you, let's look at the possibilities for domain. I am absolutely fine with you doing this. All reals, but x is not equal to minus 5 pi plus 2 pi k. Totally fine. Even though that's not the first non-negative asymptote. The homework, most of the time, we'll have to check. I think always it wants the first non-negative asymptote. I forget if it will accept equivalence. You could also write this. Negative 3 pi plus 2 pi k. So the 2 pi k is the indicator that the asymptotes are 2 pi apart. And then we have to put the counter on there. That's totally fine. You could also write, if you go 2 pi more, negative pi plus 2 pi k. That's true. So if we just keep jumping over, there's going to be an asymptote here at negative pi. The first positive, or the first non-negative, which in this case is positive, asymptote is going to happen at pi. That will be where the first, the homework, if it really wants the first non-negative, would write it as this, x not equal to pi plus 2 pi k. All of those are equivalent. They're just starting in a different asymptote. For this one right here, this is the k equals 0 asymptote. And then that's k equals 1, k equals 2, k equals 3. For the other ones, they're just moving to the right. For this one, the first asymptote we're counting, this one is k equals 0, etc. So it doesn't matter. But if you want the first non-negative asymptote, if you want to stick to that convention, then that's the one that you would want down there. On the test, I don't care because they're all true. They're all equivalently true. They're all the same. They're all equivalent. Doesn't matter. Okay, any questions on how we did that?
So tan is always pi, right?
The basic period for tan is always pi. The basic period for cotan is always pi. The other 4, basic period is 2 pi. All right, let's take a look at cotan. So we looked at this basic graph last time. And one thing to notice right off the bat, you can't quite see that there's an asymptote right there, but there is an asymptote there. Notice that your first period is from the y-axis to the right, just like sine, just like cosine. Tangent is the only oddball. Tangent is the only one where the first period goes a little to the left of the y-axis. All the other ones, the first period is to the right of the y-axis. So there's our first period, just to the right of the y-axis. So this one, we'll do the same thing that we did with sine and cosine. Find the phase shift, add the period. They'll be the same. Domain. What's the domain for this one? Looks like all reals except the asymptotes. The asymptotes are pi apart. All right, that's pi. So how's our counting thing going to go here?
Pi plus pi k.
So you could do pi plus pi k. That would absolutely work. Usually they would do the first non-negative, so they would do 0 plus pi k. But then you don't even need to put the 0 in. 0 plus anything is itself. So we just actually have the simplest way would be to do pi k. That's the simplest way. When k is 0, that's here. When k is 1 pi, you're here. When k is 2, you'd be at 2 pi. So that'd be the simplest way. It's just pi k. All right, so transformation here. Let's see. Yeah, I'll go through this with you. So reflection, yes or no? No. Amplitude, not applicable. So period. Cotangent, basic period is pi. And then we have to divide by the leading coefficient of the angle. What's that leading coefficient? 1. So the period of this transformation is just pi. How about phase shift? pi over 4, opposite of what we see. It's already factored. There's no coefficient to factor. Vertical shift is 3. All right. So again, start with phase shift. And I'm going to put my shape up here. So the shape for a cotangent is down to the right. That's our shape for cotangent. Down to the right. Start at our phase shift, pi over 4. Let's get that on the graph. Okay. And then the period. Just like sine and cosine, just add it to the phase shift. Tangent is the only one where the period is on the midpoint. On the phase shift as a midpoint. So we have to add the period to the phase shift. So 5 pi over 4. Everyone okay with that? And what's that middle point going to be? Let's see. So if we add these and divide by 2, we'd have pi over 4 plus 5 pi over 4 divided by 2. So we'd have 6 pi over 4 times 1/2. So 3 pi over 4. 3 pi over 4. Is that what you said? 3 pi over 4. So that's the midpoint. We don't need to subdivide those. With a tangent, it's only the midpoint where there's a key point. So at most, we would just need to find that center point. Okay, so center line normally would be here if there's no vertical shift. But lo and behold, there is a vertical shift. So we've got to go up and down. Well, not down. For cotan or tan, we would just go up 3. So our center line is jacked up to 3. Don't have to deal with above and below the center line for a tan or a cotan. You can ignore that. Last step is the reflection and the shape. Okay, so we know that there are asymptotes at either edge. And we know that there is a key point right there. Since there's no reflection, down to the right. Down to the right it is. Again, it doesn't really matter how steep you put this in here. I'm not going to grade you on that. So we'd have that. All right, domain of this function. We wish it was just all reals, but it's not. How far apart are the asymptotes? What's the distance between them? Pi. So x cannot be equal to... Yep, exactly. No, x cannot be pi over 4 plus pi k. It'll take away the asymptotes. And range all reals. So any questions on cotan? So the two things to keep in mind with cotan. Basic period is pi still, like tangent. But different from tangent, phase shift, add the period to it. All right. Let's look at our reciprocal functions. These are remarkably easy. If you can do sine and cosine, you can do these. And I believe that we've done enough of sine and cosine. We'll find out. To do these, you have to be able to do sine and cosine. For cosecant, we looked at this a little bit last time. There is the first period of sine. And this is the first period of cosecant. So if you want to graph the first period of cosecant, graph the first period of sine, and then graph those two u's. This one, if you want to graph secant, you graph the first period of cosine. And so we'll call that a guide. And then here we have a couple of broken u's, and then one upside down u. All right. So the period for both of these is 2 pi. And you can see that pretty clearly because we're basing it off the guide of a sine or a cosine. Those have period 2 pi. The reciprocals will have period 2 pi. The domain for this one, all reals except x cannot be. Again, we have an asymptote. You can't see it maybe right there in the graph, but there's one right there. So pi k. Asymptotes always seem to be pi apart. The basic functions that have them. Range, oops, not all reals. Range goes from minus infinity up, and it stops at -1, and then picks up again at +1. Similarly, over here, we look at our first asymptote. That's at pi over 2. First non-negative is at pi over 2, so x cannot be pi over 2 plus pi k. Range, same as the other one, negative infinity to -1, union 1 to infinity. Okay, so there are the basic cosecant and the basic secant, the green functions. So let's graph one. Cosecant. All right, let's factor first. We'll have 3 cosecant. There's a leading coefficient of 1/2. X divided by 2 means the coefficient's 1/2. So we're going to put the 1/2 in front of the angle. And that will be x minus pi. And then a vertical shift of 1. Okay. So here's the guide function. For the guide, we're going to choose the reciprocal of cosecant, which is sine. So we're going to write this as 3 sine 1/2 x minus pi plus 1. So that's going to be our guide. These characteristics will be for the guide. If we were looking at amplitude, would it make sense to talk about amplitude for cosecant or secant? Amplitude, by definition, is the maximum distance above or below the center line. And if you look at either cosecant or secant, they go up forever and they go down forever. So it doesn't make any sense to talk about amplitude for secant or cosecant. But we have to draw the guide. And the guide definitely has an amplitude. So when we put amplitude here, it's going to be for the guide because we have to start at the guide. So that A will be for the guide. We factor, and now we go right through our characteristics. Reflection, no. Amplitude, 3. It's the absolute value of the leading coefficient. Period, 2 pi over 1/2, which is 4 pi. Phase shift, opposite of what we see. Vertical shift, exactly what we see. And we're good to go. Any questions on the 5 properties there? Good? So we jump to our sketch. X-axis. Where do we start? What characteristic do we start at first? Phase shift. Go to pi. And then, second step, period. So what's the right endpoint have to be? 5 pi. And for a sine or a cosine, we'll subdivide into 4. It looks like they're just pi apart, right? So 1 pi, 2 pi, 3 pi in the middle. So if they're all pi apart, we can stick in the y-axis pretty accurately. there. Okay, vertical shift is next. Vertical shift is step 3. That tells us where our center line is going to be. So that's at 1. So our center line, maybe about right there. Amplitude. So we have to go up 3 and down 3 from there. -1, -2, -3. And 1, 2, 3, what's that? 1, 2, 3, can't count. 1, 2, 3. So that brings us up to 4. We don't need that one. Oh, wait, the amplitude, why did I go to -3? Where do we need to go down to? Just -2. Yeah. We can go down as far as we want, but we only need to go to -2. Let's get that extra one off there. All right, shape. So for sine, that's our shape. And the shape for sine has those 5 key points. And nothing's going to change here for the 3 on the center line. And does anything change for the 2 midpoints? No, because there's no reflection. So at this midpoint over here, we're going to be up at 4, and this one we're going to be down at -2. And we're going to graph this one with dashes or dots or whatever. This is not the graph we're really wanting. We want cosecant. So here, so up to now we've done nothing except all we've had to know is that the reciprocal of cosecant is sine. That's all we've done so far. Other than that, this is all stuff we did previously. So now here's what we do to finish it off. Wherever the center line is crossed, we are going to have a vertical asymptote. Wherever the center line is crossed, we have a VA. And now we just have to throw in those arches. And we're good. So let's use black, I guess. So we have this arch, an up arch here, a down arch there. And these asymptotes go on forever. It kind of looks like I'm saying it crosses the asymptote, but it doesn't. It just gets super close to that asymptote. But they're definitely constrained on either side. That is the first period of our transformed cosecant. So if you can graph sine, you just throw in your asymptotes, throw in your arches, good. And we have a little bit of thinking to do here for domain and range. The domain, all reals but the asymptotes. So let's make sure it's clear how far apart the asymptotes are. Looks like they're 2 pi apart. So x is not equal to, what's our first non-negative one? Pi plus 2 pi k. Range. Range y-axis, start down below, coming up. Stops at -2. No range values until you get back up to 4. So -infinity to -2 inclusive, bracket, union, 4 to infinity. So elegant, this trigonometric graphing stuff. Now it's your turn to demonstrate the elegance, to experience the elegance. All right, so you guys try that one. Secant. B1 with the elegance. So there is no Dylan here, is that correct? I'm going to drop him today. First potential landmine. Yeah, that's what I'm saying. Think about distribution. Certainly the two exponentials, but 2 times 5 is not bad. So here is that scenario where you're going to put 2 as the 1. So now it's Yep, exactly. Right. So your period is always going to be to right of that level. There's the guide function up there. Do you have any guide issues? Any guide issues?
Well, we got the
Same issues. Oh, that's easy. Let's say once, right?
We'll kind of move it out here so that way we cover like.
Bang. And I don't know. Okay, so period for cosine. So your guide function is cosine. Period for cosine. Basic cosine is 2 pi. So it's equal to 2 pi divided by that period in S1. So 2 pi divided by 2. So just dividing by the leading coefficients of the unit. So it's 2 pi divided by 2.
Yeah. So this is still, so I guess we still has these beats here.
Yeah.
That's a little bit different than this.
Yes.
We're going to do that for sine.
Cosine.
I mean cosine.
Yeah. Cosine shape is the U. U-ish. That's the U with wings. Yes. It's the bird.
So 2 pi, yeah. 2 pi is cosine is under all 4.
phase shift? Oh, the multiplication right there?
Yeah, for this, yeah. How we got this.
Yeah. Okay, so here's how I would write it. If you're not sure how to factor it, you're trying to factor 2. So here's what I think you can do to help yourself. If you're trying to factor a 2 out and there's no 2 there, put a 2 there. But if you put a 2 there, you have to multiply the denominator by 2 also. And now when you factor out a 2 across the top, 2 comes out leaving x, and the 2 comes out there leaving pi over 4. That make sense? And the other way to think of it,
I would just do.
the other way to think of it is if you factor, if you have pi over 2, which is 90 degrees, if you want to factor a 2 out of it, you're basically saying what's half of pi over 2? Half pi over 2 is pi over 4. Right? All right, yes or no on reflection? Yes. Amplitude for the guide. 4. Period. 2 pi over 2 is pi. Phase shift. Negative pi over 4. Vertical shift. 2. All right. Step 1, we look at the phase shift. So we're going to go to minus pi over 4. All right. And then what do we do with the period? So we start, that phase shift is the left endpoint. To get to the right endpoint, we add the period. So we're going to add pi to that. And what's negative pi over 4 plus pi? 3 pi over 4. Divide that into 4 equal pieces. And you should see that each piece is pi over 4 in width because we took the period. If we divide the period by 4, each of those is going to be pi over 4. So that tells me exactly where the y-axis is going to be. It's going to be right there. All right. Vertical shift is 2, so that's going to take our center line and lift it up 2 units. So I'm going to put 1, 2 right there, and that center line is going to be lifted up 2 units. And then how far above and below the center line do we go? 4 above, 4 below. This one takes us up to 6. And this takes us down to negative 2. Now we look at our shape. So we just use the amplitude. We look at our shape in conjunction with reflection. And we see that normally our bird here has 2 points up top at either end, but because there's a reflection, those 2 points are going to be down below. So one of them is going to be right there, and one's going to be right there. And there's going to be one right in the middle up top. So instead of a V, we're going to get an upside down V. And at our 2 midpoints here, we're going to be right on the center line at the 2 midpoints. So we get those. And graph this with dots. Get that. Wherever the guide crosses the center line, we have an asymptote. So we have an asymptote right on the y-axis, and we have an asymptote over there at pi over 2. Now we put in the arches. We've got a full arch right in the middle. Let's use a different color right there. We have a full arch right there. And we have a couple of broken arches. There and there. That'll be our first period of the transformed secant. So that's the first period. So if you're being asked for the first period, you don't want to put these extra, you don't want to complete those arches there if you're only looking for the first period. The first period does not include that. So you've got to have 2 half arches there. How about the domain? We would need to know how far apart these asymptotes are. How far apart are these asymptotes? What was that? Pi over 4 apart? Pi over 2 apart. Because each of these little subintervals is pi over 2. So it takes 2 pi over 4s, which make a pi over 2. Or you could say that the period of the function is pi, and there's an asymptote every half period, essentially. All right? So our first asymptote is right at 0. So we can just say all reals, but x is not equal to pi over 2k. And then range, minus infinity, climbing up the y-axis to -2. And then we have to make a big jump, quantum leap, up to 6, and then up to infinity. See you Thursday.
And there's tutoring Thursday morning.
Tutoring Thursday morning across the hall, 9 o'clock. Graphing practice. Will be good practice.
Is there still tutoring Friday?